All right, so a couple things before we go ahead and get started. And I've still got them up on the board over here, like the most important items of the week. If in here or another class, a weighted course, upper level, if you happen to have unfortunately failed it for the first 6 weeks, you can get a waiver so that you can continue to participate in athletics or whatever other activity you belong to. They're going to be due to Marcia Edwards Friday by 10 a.m. We are having a tornado drill Thursday during second period. So have your second period teachers started talking to you about it? Nope. Okay. Well, maybe they're saving a surprise. I don't know. But what would we do in here if a severe weather drill happened?
Go down to the ground.
Okay. So we're going to go to the main hall through the 1200 hallway right below us, past the computer classrooms. Right down at the end, you have the art office across from the, yes, sir. The basement is not that large. In fact, there is no possible way we can fit everybody in the school in the basement. Yeah.
So why not put like half and half? Like make sure we have
I don't even think it would hold half our population. It's not that big a basement. I mean, we'd be pretty packed down there, but then how would you decide what half goes down and what half gets to stay up in the weather? Upperclassmen go down? Okay.
Yeah.
There you go, upperclassmen. Freshmen are beating on the door. Wait! Okay. Anyways, but where the 1200 hallway and the main hallway on the first floor intersect, right there's the art office across from those vending machines. So right there is where we would go. Okay, Thursday we got a quiz coming up. So we are going to be continuing this week. In fact, I'm thinking that pretty much this entire week is going to be spent talking about the chi-squared test for independence, because there is a lot to unpack here and talk about. But on Thursday, we're going to have that quiz. It's going to be over linear regression. Okay, the homework we just turned in, so I'll be asking you about the correlation coefficient. I'll be asking you to find your trend line, probably make a prediction, and then make some kind of comment as to whether, that's going to be a valid prediction or not. Okay. And then we have just under 2 weeks until our first exam. It's going to be on Monday, October 8th. So it'll definitely have chi-squared, and more than likely we'll also include items from our next unit. We're going to talk about logic sets and probability, probably intersection, union, all that good stuff. Okay, any questions about anything that's going to be happening? No? We're good? Okay, well, let's go ahead and get right back into it. We were talking about chi-squared test for independence. And what do we call this two-way table right here? You call it a contingency table, okay. So when you take your data and you go ahead and kind of subdivide it itself, so we have, both genders, male and female, but here we're also talking about exercising regularly and not exercising regularly. So your totals for your columns and your rows need to match up for the total amount we have in the study. In this case, we were talking about 400 people. And I think, let's see how far we got. We started talking about the observed values, which is your original data, versus the expected values, okay? What you do is, if I want, say for example, the number of males who exercise regularly, if I want the expected value for that, I'm going to take the total in that column, multiply it by the total of that row, the 216 times 208, and I'm going to divide it by 400. Okay, so based on the observed, well, what can we expect? I can expect, let's say, 112 males to exercise regularly, okay, based on the data that we collected. All right, and I think, is that as far as we got? Did we just go ahead and fill in the table? And we're pretty much done with it? Okay. All right, so now let's go ahead and start talking about the chi-squared test itself. It examines the difference between the observed values we obtained from our sample and the expected values that we just talked about how we calculated. So our chi-squared calculated value, this is what we're trying to determine, is, what's this sigma notation? It's the summation of the square difference of the observed values and the expected values. So F naught, F sub O, is the observed. That's our original data. F sub E, that's the expected values, our frequency here is we're calling it. So you take the sum of that square difference divided by the expected frequency. Now, if the variables are independent, the observed and the expected values are going to be very similar. This means that the values of the difference will be small, and hence the value that we're trying to calculate is going to be small as well. If the values are not independent, the observed values will differ significantly from the expected values. This means that the difference will be large, and hence the value that we calculate will be large as well. So we're going to, for a very short time, kind of run off this idea that we have either a small or a large value, but it really doesn't tell us a whole lot when we want to get very specific. Like, how large would be too large? Okay. At what point would we go ahead and say the number that we calculate is too large, and I can no longer say they're independent? I would say they're not independent. And this is kind of where we ended up yesterday. The good news about the chi-squared test for independence, okay, whatever quantities you happen to be comparing, it can give you a really good indication if there's some association between them, if there's some relationship. Okay, the bad news is it will not tell you what the nature of that relationship is. That will be something that you'll have to go ahead and come up with on your own, and hopefully use the data to kind of strengthen your point of view. Okay, so let's take what we have here. And that's putting a lot of green on screen, so let me see if I can. Okay, then I will do this with the mouse. See if I can pull that down a little bit so I can see the top. Did anybody else need the key from yesterday? Everybody else is okay with the key for the linear regression? Okay. Did anybody need the key from the statistics review we did on Friday? Okay. You guys are energetic today. I can feel the electricity. Okay, let's move past this awkward moment and move on with our notes. Okay. Let me get my, where did I put my, oh, here they are on top. Okay, so here is how we're going to go ahead and calculate this. Now, if you're going to do it by hand, you know, a lot of these statistics problems, we've used these tables to go ahead and kind of make things easier to organize all of our information. So let's go ahead and start with our observed data. So we're going to use this idea still of gender versus regular and non-regular exercise. Okay, so let's see what my observed were. Let's see, it was 110, 106, 98, 86. So 110, 106. And you're going to have to help me with this. 110, it was 106, right? 98, right? 98 and 86, yes. Okay, so the first column in my table is going to represent the observed data. This is what you would have collected, or somebody at some point would have collected. Now, remember what we did yesterday, we just talked about how to find the expected values based on those particular cells. Okay, now you want to make sure that when you're doing this, okay, you line these up correctly. So for example, 110, okay, was in your top left corner, right? This was originally 110. So you want to make sure to put the expected value that corresponds to that. All right, so we have 112.32. So 112.32. Okay, and then for 106, we should have gotten the 103.68. All right, 98 would have given me 95.68, and we finish up 86, 88.32. Okay. Is everybody okay? All right. Well, now we just want to go ahead and take the difference of those. So somebody help me out. 110 minus 112.32. Okay, so negative 2.32. Perfect. Now I need a 106 minus 103.68. 2.32. Okay. What about a 98 minus 95.68? 2.32. Okay. And you'll notice if you do work more of these problems by hand, you're going to be able to notice patterns, okay, such as these. What's the last one here? 86 minus 88.32. Negative 2.32. Okay. So this next column here is just going to be the same value over and over again, because it doesn't matter if it's positive or negative. When you square, okay, a value, it's going to be positive, right? So what is a 2.32 squared? Okay, now I put 5.3824. Do you want me to go ahead and round it to two places or the 4 to 2? Okay, so let's say 5.38. So make sure that looks like a 5. 5.38, 5.38, 5.38. Well, here is where the change is going to occur because I'm now going to take this square difference and do what? I'm going to divide it by its respective expected values. Okay, so I want to take 5.38 and divide it by 112.32. What should I be getting? Okay, 0.0479 is what I got. You just want me to go ahead and round to two places again? Okay, so 0.048, perfect. All right, so this one we'll go ahead and round to 3. So now I need 5.38 divided by 103.68. 0. Point what? There we go, 0.052. And then if you go ahead and do the same thing for the others, 5.38 divided by 95.68, I got 0.056. Would you guys agree? And then divided by the 88.32, I got 0.061. Okay. Would you guys agree with that? Okay. Now we just need to take the sum. Okay. 0.217. There's my chi-squared calculated value. Okay. And of course, you can see that right there on our nose, but it doesn't make up, which is very small. That indicates that gender and regular exercise are independent. So what this is saying is that we came up with a value that was so small, there's no association between gender and our regular exercise. That means there's no relationship, at least according to this data right here. That's what we're looking for. But this is what I was referring to a second ago, and we're going to start to build on this today. I mean, how large is too large? Okay, this is what I was referring to a little while ago. At what point do we go ahead and say, okay, it goes from being independent to actually having a relationship? And there's a couple of factors that we're going to look at that's going to help me with that. But let's go ahead and practice a few ideas before we move on with that. Okay, we'll kind of put that to the side. I want to go ahead and construct an expected frequency table for the following contingency tables. So we have no idea what the observed data is, right? The original data that was taken, and that's okay. We don't need it. What's all the information I need if I want to come up with the expected frequency values? I just need the sum, the column total, the row total, and then the grand total of everything that was involved here. So, for example, if I want to figure out, we've got two rows here, people who like fish, dislike fish. Then we have like chicken and dislike chicken. So for this cell right here, let's say they like fish and they like chicken. What am I going to do to figure out the expected frequency value? Okay, so I'm going to take 75 times 60 divided by 100. So somebody help me out with that. What am I going to get if I were to put that in my calculator? Okay, what's that? 45 is what I got. Okay, so that's how I want to go ahead and find the expected frequency value for people who like fish and who dislike chicken. So I'm going to multiply 25 times what? 60. Again, divide that by 100 because that's the grand total in my survey here. And what's that give me? I'm getting 15 out of that. Good. Is there anybody who's having trouble seeing where we get these expected frequency values? Okay. So what can we say about this? You know, again, just kind of not worrying about the fact that we don't have the observed values. We can say that we would expect out of the 100, 45 people to like both fish and chicken based on the data that we had originally taken. Okay. Has anybody already figured out dislikes fish and likes chicken? I got 30. 75 times 40, this time divided by 100. And what about dislikes fish and chicken? 10. All right. Okay, good, 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 good. Okay. Well, let's go ahead and take this one here. Now, the difference in the next one is that this is my observed data. This is my observed data. This is the data that was collected. So it looks like we have data on junior, middle, and high school students who play sports and who do not play sports. How many total were in the survey? 250, okay. So we were talking yesterday also about the dimensions of these. What would the dimension of this one be? How many rows by how many columns? 2 by 3, there we go. The one row and the one column that we don't include in that is going to be those sum totals. There you go. All right. So let me go ahead and give you about 30 seconds to a minute. These are the observed for each of these 6. Go ahead and calculate what the expected frequency values would be. So what was recorded, we have 35 junior school students who play sports. In order to find the expected value, I'd multiply what 2 values? Okay, so 58 times 165, we want the intersection for the cell we're looking at, and then we divide that by 250. Okay. And then as you get them, I rounded mine to 2 decimal places, so if you want to do that, that's great. Who's got the first one? 38.3? Perfect. Okay. 38.3. Okay. All right. Has anybody got middle school who play sports? Middle school who plays sports. Okay, 56.8. Perfect. Next up, high school who plays sports. Okay, now this one's 69.96. That's close enough. We could probably just go ahead and say 70 on that. Okay, I think that'd be acceptable. Now, who do not play sports for junior school? 19.7. Perfect. Okay, next up, the 27. Okay, middle school who do not play sports. Hello.
Libby Hampton in here this period.
Who?
Libby
Libby.
Hampton.
Libby. Okay. Speak to you real fast. Okay, so what's up for middle school who do not play sports? 29.2. Perfect. And then what about the last cell there? Okay, I'm getting 36. In fact, I originally got 36.04. There you go. And are you noticing anything with the expected values that we're getting? Okay. Like, for example, what's 70 plus 36? Still gives you 106. And it's just a matter of rounding, so that should still be pretty accurate. Okay. Is anybody having trouble finding the expected values? Okay. Everybody's okay with that? Okay, good. Good, good. Now remember, I'm going to show you how to do all of this in the calculator, but there's just quite a bit to get through by hand before we go ahead and get there. It's still probably going to be a day or so before I show you that. Okay, so let's say this. Consider the contingency table. So we're going to go ahead and divide it up again into males and females who pass a math test or who fail a math test. How many total were surveyed? Okay, 100. So it says construct an expected frequency table. Interpret the value in the top left corner of the expected frequency table, and then calculate our chi-squared value by copying and completing this table. Well, it's already copied for you. We just have to complete it. Okay. So let's go ahead and construct an expected frequency table. So instead of creating another table, I'm just going to write on this one as I did before. So for the number of males who pass a math test, I'm going to take 60 times 50 and divide it by 100. How many should I be looking at? 30. Okay, so what I'm writing down are my expected frequency values. So based on the data I collected, I can expect 30 males to pass a math test. Okay. And in fact, that takes care of part B right there. Interpret the value in the top left corner of the frequency table. Okay. Man, do you have the next one? Okay. Looking for the number of males who failed the math test, the expected value. 40 times 50 divided by 100. 20. Okay. Thank you. There we go. And then females who passed the math test. 30. And last up, females who failed the math test. Another 20. There we go. Okay. So now let's go ahead and run through a table very similar to what we did just a few moments ago. Again, getting a little bit of practice. We see our columns here, F naught. And when we have it, I'm just calling it F naught. Technically, that's an O. But when you have that kind of notation, typically in math, we say naught, F naught. So that's the observed data. F sub E is the expected. So let's make sure we get the corresponding values. For 24 observed, we got 30 expected. 26 gave me 20, 36 gave me 30, and 14 gave me 20. Okay. So now let's take the difference. 24 minus 30. Negative 6. 26 minus 20. 6. 36 minus 30. 6. 14 minus 20. 6. 5 minus 11. Sorry, I just kind of got on the roll there. Negative 6. Oh, yeah, I was thinking about that. Yeah. Kind of ruined that with my own joke. Dang it. Yeah. That's okay. You'll laugh later. I'm sure you do, right? Yeah, I always. It's like when you walk out of class, then you just go, oh my God, it's so fun.
Yeah.
Yes, exactly. Okay. All right. So now let's square those differences. So all these are going to be what? 36. 36, 36, 36, 36. Okay. Now I want to go ahead and take those square differences and divide by the expected values that we calculated. So I need 36 divided by 30. 1.2. So for both of these, 1.2 and then 1.2. And then I need 36 divided by 20. 1.8. Yes. 1.8. 1.8. So let's add all those up. 6. Now think about the last problem that we were looking at. We ended up with a 0.217, I think, on the first problem we were looking at, which was really small. So we said, okay, because it's so small, these cannot have an association. They have to be independent. Well, compared to the 0.217, this is much larger, right? But again, it goes back to that original idea that I was throwing out there. At what point do we go ahead and say, okay, this value has become large enough that I'm going to say they're not independent. Now they are independent. Does that make sense? Okay. So we got to figure out what to do with that. As far as calculating it, is anybody having an issue? Okay. So we're good on that? Okay. So let's talk about a couple of ideas. There are two items that are going to help me determine exactly what value, where they're going to change from independent to not independent. Okay, we've seen that a small value of chi-squared indicates that the two values are independent, while a large value of chi-squared indicates that the variables are not independent. We will now consider a more formal test which determines how large chi-squared must be for us to conclude that the variables are not independent. This is known as the critical value. Okay, this is the value we're going to go ahead and determine. This is the turning point from there is no relationship between them to there is. Okay. So let's see, and it's based upon two things. The size of the contingency table, measured by degrees of freedom, and the significance level that we use. Okay, so we're going to go ahead and focus our attention for a little bit on the size of the contingency table. So I'm talking about the dimensions. But when you're talking about the dimensions here, because we're adding up the columns and the rows, we have what's known as degrees of freedom. It says in a contingency table, the number of degrees of freedom is the number of values which are free to vary. Okay, consider this 2x2 contingency table alongside. Now, instead of just reading this, word for word, because that's going to get boring, and math is never boring. In order to calculate your degrees of freedom, you need to take the number of rows minus 1 times the number of columns minus 1. Okay. That's going to give you what we call degrees of freedom. Okay. So let's take a look at this here. All right. What's the dimensions of this table? Remember, 2 by 2, 2 rows by 2 columns. The one row and the one column that we don't include in that are going to be the total row and the total column. Everybody's okay? So it's a 2 by 2, right? So I have 2 rows minus 1 times 2 columns minus 1. So it looks like I have 1 minus 1. So my degree of freedom is going to be 1 here. Now let's think about what that's really saying. I've got these 4 blank spots, right? What that means is I can choose any value, of course, within reason. It can't be anything. It has to work with the totals that I already have. Like, for example, like this one can't be more than 15. Okay. But once I choose a value, what they're talking about right here, the example they give is 9. Like, as soon as a value is chosen, do I have freedom to put whatever numbers I want in the other cells? I don't. Because take a look. Okay. If I know that this row total is 12, then this one has to be what? Has to be 3. See, I'm only allowed to put in one value because that's what my degree of freedom is going to tell me. Okay. So once I plug in this 9, this B2 has to be what? 6. See, the table starts to fill itself in. See, I no longer have a choice. And this one would have to be 2. Okay. So depending on the size of your contingency table, you'll have a different degree of freedom. That's how many cells you are able to put in yourself before you can't choose anymore. Okay. The table is going to take over. All right. And I believe even down here it was talking about this one. So this one is a 3 by 3, right? Okay. So 3 minus 1, the number of rows minus 1 times the number of columns minus 1. So here we have 9 blanks, right? My degree of freedom for a contingency table this size would be 4. I can plug in any 4 numbers I want, but starting with the 5th one, I no longer have a choice. Okay? So let's do this. Out of these 9 right here, just choose 4 at random. What 4 do you like? Okay, so this 5 right here or the bottom right? Bottom right. So we like this one here, 5. 4 in the very middle. Okay. 6 in the other corner. And one more. 2 to the right of 4. 2 right here. Okay. See, when I first start to fill in the table, there's different ways I can fill them in because I could choose any 4 values I want. Again, within reason, looking at the totals that I already have. But once I filled in 4 on this 3 by 3, see, I no longer have a choice now. Can I put any number that I want right here? No. See, because of the column total 11, it has to be what? It has to be 4. See, the table starts to fill itself in. Is everybody okay on the concept of degrees of freedom? Okay. All right. Louise, did you have a question? Or? Oh, I thought you raised your hand for a second. I'm sorry. That's right. Okay. So if we go ahead and start to look at the rest of it, it's almost like, just a little puzzle. 6 plus 5 plus what is 13? The 2. And I mean, we see the table over here, but you can start to see how we generate it. Okay. So everybody feels confident about the degrees of freedom. Okay. Well, the degrees of freedom work with what we call the significance level. Okay. Both of these work together to decide what your critical value is going to be. Right, Peyton? Right, Libby? Okay. Okay, there we go. I just want to make sure. Eyes are open because I can't see overhead. Okay. All right, so as the chi-squared value gets larger, it becomes increasingly unlikely that the variables involved are going to be independent. The significance level indicates the minimum acceptable probability that the variables are independent. That means there's going to be no relationship between them at all. Okay, so we usually choose one of these 3, 10%, 5%, or 1% for the significance level. And what's the difference between the 3? It really just depends on how lenient you want to be with your data or how much more specific you want to be. Personally, I always kind of choose the middle of the road. I go 5%. Okay, but if maybe at 5% you don't get the results that you're looking for, maybe go to 10%. Give yourself a little more leeway. If you want it to be more specific, now if you're dealing with data that, let's see, what's a real world application I can think of? Like maybe if you're talking in the medical field where data is very closely related to people's lives, I would want to be as specific and accurate as possible. So maybe with something like that, I would probably go 1%. Okay. But really, I mean, there's no right or wrong answer. It's really just what you decide you want to use. Okay. So anybody who wants to use the chi-square test for independence on your IA, for instance, okay, if you decide to do this, maybe part of that could be just putting in there why I decided to use 10%, or why I decided 5% was better than 10%, whatever the case is. Okay. So for a given significance level and degrees of freedom, remember how we just calculated that. The number of rows minus 1 times the number of columns minus 1, those working together in this table are going to provide you with your critical value. Now the value we come up with, our calculated value, we compare that to our critical value. Okay? And that's going to determine yes, there's a relationship, or no, there's not. Okay? Now, will you have to memorize this table? Yes. Well, he's already like, he probably already figured I'm messing with you, right? You do not have to memorize this table. Okay. Thought I'd see a lot more people go, whew. Anyways. Now, what's going to happen on these will appear on the paper exam, but usually when they ask you a question about chi-squared, they're going to be providing you a lot of the information. They won't provide you the table in, say, the math booklet or the problem, but what they will do is say, we want you to test this at a 10% level with a critical value of, and typically they're already going to provide you with that. Okay, so what I will more than likely do for like a quiz or a test, I'll either have a copy in addition to that of this table prepared for you, or I might even have it on the quiz or test itself. Yeah, but you are not required to memorize that. That would be ridiculous. Okay, so let's say, for example, what they have here, let's say they choose a significance level of 5%. Okay, and let's say they're ending up with a 2x2 contingency table because they got degrees of freedom of 1. Okay, so what you do is we have a degree of freedom of 1, and we chose 5%, so you just look to see where it intersects. The critical value I want to compare my calculated to would be 3.84. Okay, so it's super simple. That's how the two items get you your critical value. Let's say I chose to go with a 10% significance level, and I had a degree of freedom of 7. Well, what's my critical value that I'd be comparing my value to? 12.02. Degree of freedom of 7 with a 10%. Just look for where they intersect. Okay. So this answers the question that I asked, several times today earlier in the lesson. Well, how do we know at what point it changes? Okay, how large is too large? Well, we compare it to this critical value that we're going to find based on the significance level and the degrees of freedom. Okay, so there's still quite a bit more to talk about. That's why I'm thinking it's going to take us all week. How are we doing so far? Does anybody have any questions on chi-squared? We're good? Okay. Peyton, what do you think? It's great? Okay. Libby, what do you think? It's good? You are? There we go. Hillary, what do you think? Just yes. All right. There we go. That's good. All right. So let's see here. Very important. In order for chi-squared to be distributed appropriately, the sample size n must be sufficiently large. Generally, n is sufficiently large if no values of the expected value table are less than 5. And that actually is a problem that I'm going to show you how to fix once we finally feel comfortable with chi-squared. If any of your expected frequency values, any of those numbers in the cell that you calculate are 5 or less, we probably want to do something with the data to make sure that doesn't happen, because otherwise it's possible we may not get accurate results. Okay. Now this right here, I'm going to come back to this. This is what we call the p-value, but I'm just going to go ahead. Let's get right to an example, and let's see what we think. Okay. Let's actually take all the information that we've walked through for all these, the expected values, talking about degrees of freedom, significance level, critical value. Let's go ahead and put it all together. All right. So step one, we have what we call the null and the alternative hypothesis. This is where you have to actually make a complete sentence. Okay. Now, the null hypothesis, this is a statement that the two variables being considered are independent. That means there is no relationship. So besides independent, another word that I would think that IB is really looking for would be association. Okay. So if they're independent, there is no association. Okay. So maybe I'll go ahead and put that here so we can have it on our notes as well. Okay. I think relationship would probably be okay, but they'll probably want to go more so for the terminology. So I would probably stick with independent, not independent, or at the very least association. Now, the other one, H sub 1, is what we call the alternative hypothesis. This is a statement that the two variables being considered are not independent. So that means there is an association. Okay. They're not separate from each other. There is some kind of relationship here. Okay. There is some kind of association. Okay, so with that in mind, let's go ahead and take a look at our problem. So step one, I want to go ahead and write out my hypotheses, the null statement and the alternative. Okay, so it says a survey was given to randomly chosen high school students from years 9 to 12 on possible changes to the school's canteen. And does everybody know what that's referring to? The cafeteria. Okay, so we're talking about the cafeteria. The contingency table shows the results at a 5% significance level, and this is usually pretty common. In these word problems, they'll go ahead and choose a significance level for you. Okay. So at a 5% significance level, test whether the student's canteen preference depends on the year group. Okay. So here's how I always kind of think about it. What's the name of this strategy? Chi-squared test for independence. So when you're writing your two statements, if you ever confuse the two, which one's independent, which one's not independent, chi-squared test for independence. The first statement is independent. Okay. I don't know if that kind of helps out. Okay. But I need a complete sentence saying that these two ideas are independent of each other. And what are we talking about again? Okay, so we're talking about the school cafeteria and the students' what? Okay. Now, should we go ahead and say preference? Should we go ahead and say something about their years? What do you guys think? Okay. So I need a complete sentence. Anybody think they got one that'll work? I'll tell you what, this is where we'll go ahead and stop today. We'll get our two sentences because I'm already seeing 202, and there's no way we're going to finish this problem before we leave. Okay, but at least we can write our sentences. Okay. Now I know what I put. Okay. Would anybody like to try and give me a sentence? Or maybe on this first one I can help you out. Okay.
Just a quick question.
Yes.
Would the hypothesis be like an if-then statement, or?
No, not necessarily. That's going to be a different concept. Then we're talking about if-then. We're talking about what's known as implication, and then we start getting into equivalence. So that's very much related, but it is a different idea. Okay, so here's what I put for the original statement. I said the student's canteen performance preference, I'm sorry, I don't know why I said performance. Canteen preference is independent of the year group. Because what items are going to make up my contingency table here? Well, we're talking about the year group, whether 9 through 12, and then our preference on what happens in the cafeteria. Do we change it or do we not change it? Okay. Now, here's what's really nice about these sentences that you're going to write. As soon as you get the first one down, the null hypothesis, what is only one thing you need to change for the second sentence? There you go. You could say the exact same thing, but just put is not independent of your group. Okay. So students, canteen, preference, and I'm going to go ahead and abbreviate this, PRF, is not independent of year group. Okay. All right. And that, I've even seen questions on the paper exams where they may ask you to go ahead and write the null and or alternative hypothesis statements. Okay. So you always want to make sure those are complete sentences, use the appropriate vocabulary, and things of that nature. Okay. How are we doing with chi-squared so far? Okay. It's kind of funny that we've been looking at this for about a day and a half now, but we still have not actually completed a full problem. There's just so much here to talk about. But if you have questions, let me know. Okay. I'll go ahead and stop it there. Looks